For over a century, physics declared faster-than-light travel impossible. Einstein's equations built an unbreakable wall around the cosmos. Nothing moves faster than light. Case closed. Except physicists just found something extraordinary buried in Einstein's own mathematics. Not a way to break the speed limit. Something stranger. A way to make the limit irrelevant. Recent theoretical proposals suggest spacetime itself could be compressed and stretched in ways that would carry a spacecraft across the universe without violating a single law of physics. The catch? These solutions introduce constraints so severe they make the original speed limit look trivial. What scientists discovered reveals something profound about the architecture of reality itself. If you want to understand why the universe guards its speed limit with such ferocity, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. You cannot travel faster than light. This statement sounds like a technological limitation, similar to saying you cannot build a perpetual motion machine or travel back in time. But the cosmic speed limit operates at a fundamentally different level than any engineering constraint humans have ever encountered. The speed of light does not represent a barrier we lack the technology to breach. It represents a structural feature of reality itself, woven into the fabric of space and time so completely that the very concept of exceeding it contains hidden contradictions most people never examine. Understanding why this barrier exists requires dismantling intuitions about motion that served humanity perfectly well for millions of years of evolution, but collapse entirely when applied to extreme velocities. Every assumption you have about speed, distance, and time breaks down as objects approach 300,000 kilometers per second. The rules change not because physics becomes complicated at high speeds, but because the simple rules we thought governed motion were always approximations, valid only for the slow-moving world where human experience evolved. The story begins in 1905 when a 26-year-old patent clerk in Switzerland published 4 papers that would demolish over 2 centuries of Newtonian physics. Albert Einstein did not set out to discover a cosmic speed limit. He set out to resolve a contradiction that had bothered physicists for decades. The equations of electromagnetism seemed to assign a special velocity to light, regardless of how the observer moved. This violated everything Newton had taught about how motion should be relative. Newton's physics made perfect intuitive sense. If you throw a ball forward from a moving train, the ball's speed relative to the ground equals your throwing speed plus the train's speed. Velocities simply add together. A person on the platform sees the ball moving faster than you do because they see both your motion and the ball's motion combined. This addition of velocities works flawlessly for everything humans experience in daily life. But James Clerk Maxwell's equations for electromagnetic waves contained no provision for this simple addition. The speed of light appeared as a constant, approximately 299,792 kilometers per second, with no reference to the motion of its source or observer. Experiments confirmed this bizarre prediction. No matter how fast you moved toward a light beam, you always measured the same velocity for that light. It was as if you could never close the gap between yourself and a departing photon, no matter how fast you chased it. Picture yourself running toward an oncoming car. Common sense tells you the car approaches faster from your perspective than from the perspective of someone standing still. Now replace the car with a beam of light. Run toward it at half the speed of light. The light still approaches you at exactly 300,000 kilometers per second. Stand still, and it approaches at the same speed. Run away from it at 99% light speed, and it still catches up to you at precisely the same velocity. This is not intuitive, this is bizarre, and it is experimentally confirmed beyond any reasonable doubt. Einstein resolved this contradiction through a radical proposal. The speed of light is not merely a measured constant, but a fundamental feature of spacetime itself. All observers, regardless of their motion, must measure the same speed for light because space and time themselves adjust to ensure this outcome. The implications cascaded through physics, like dominoes falling. If the speed of light remains constant for all observers, then something else must give. That something turned out to be our intuitive concepts of simultaneous time and absolute distance. Einstein demonstrated mathematically that observers in relative motion experience time passing at different rates. Events that appear simultaneous to one observer occur at different times for another observer moving relative to the first. This was not a philosophical argument about perception. This was a mathematical necessity arising from the constancy of light speed. Special relativity showed that time and space are not separate, unchanging stages on which physical events occur. They form a unified four-dimensional structure called space-time, and this structure transforms in specific ways depending on relative velocity between observers. Think about what this means for your daily experience. You and a friend synchronize watches, and she boards a spacecraft. She accelerates to high velocity and travels to a distant star before returning. When she lands, your watches no longer agree. Her watch shows less elapsed time. She has aged less than you have. This is not a trick or an illusion. Time itself passed more slowly for her because she moved at high velocity relative to you. The consequences for high-speed travel proved devastating. As an object accelerates toward light speed, its mass effectively increases from the perspective of external observers. This is not mass being added from somewhere. It reflects how energy and mass relate in relativity. The kinetic energy pumped into, accelerating the object contributes to its effective mass, making further acceleration increasingly difficult. The mathematics describe a curve that approaches infinity asymptotically. As velocity approaches the speed of light, the energy required for additional acceleration climbs toward infinite values. To accelerate any object with mass to exactly the speed of light would require more energy than exists in the observable universe. This is not a technological limitation awaiting better engines. This is a mathematical impossibility embedded in the structure of space-time. Consider what happens as a spacecraft approaches 90% of light speed. From the perspective of observers on Earth, the ship's clock runs slow. Time aboard passes at roughly half the rate experienced by those watching from home. The spacecraft appears compressed in its direction of travel. Its effective mass has increased substantially. The energy bill for acceleration has already grown enormous, pushed to 99% of light speed. Now the ship's time runs at roughly 1/7 the Earth rate. Mass has increased by a factor of 7. The energy cost for each additional increment of velocity has grown enormously compared to lower speeds. Getting from 99% to 99.9% requires more energy than getting from 0 to 99%. At 99.9% of light speed, time dilation reaches a factor of 22. The energy required for further acceleration has become stupendously large. Stars have burned for millions of years, producing less energy than would be needed to push a spacecraft those final fractions toward light speed. At 99.999%, the factors exceed 700. The energy budget would exhaust stellar output. Entire suns converted entirely to thrust would prove insufficient, and still the speed of light remains unreached, forever asymptotically out of grasp. This asymptotic barrier means that accelerating through the speed of light is not merely difficult, but definitionally impossible within the framework of special relativity. The barrier is not a wall you could theoretically punch through with enough energy. The barrier is a feature of how space and time relate to each other. As you approach the limit, the very concepts of distance and time warp around you in ways that prevent the limit from ever being crossed. Imagine trying to reach a destination that moves away from you faster the closer you get. Every step forward causes the goal to recede by more than a step. You can approach indefinitely without ever arriving. The speed of light works similarly. As you accelerate toward it, the energy requirements steepen so dramatically that reaching it would require infinite energy, a quantity that does not exist. But the implications extend beyond energy requirements. Special relativity also demonstrates that faster-than-light travel would violate causality, the fundamental ordering of cause and effect that makes physics coherent. This requires understanding how relativity handles the concept of simultaneity. In our everyday experience, two events either happen at the same time or they do not. This seems like an objective fact about the universe, independent of any observer. Einstein showed this intuition is wrong. Events that appear simultaneous in one reference frame occur at different times in reference frames, moving relative to the first. The ordering of events in time depends on how fast the observer moves. This sounds abstract until you consider concrete examples. Imagine two lightning strikes hit opposite ends of a train platform simultaneously from the perspective of someone standing in the middle of the platform. A passenger on a train passing through the station at high speed sees something different. Because the train moves toward one lightning strike and away from the other, light from the strikes reaches the passenger's eyes at different times. More importantly, careful analysis shows that from the passenger's reference frame, the strikes genuinely occur at different times. Neither observer is wrong. Simultaneity itself depends on motion. This relativity of simultaneity has a remarkable consequence. For events separated by space-like intervals, meaning they are far enough apart that light cannot travel between them in the time separating them, different observers can disagree about which event happened first. Some observers might see event A occur before event B. Others might see B before A. Neither is wrong. The time ordering of space-like separated events genuinely depends on the observer's motion. Now imagine a faster-than-light signal connecting two distant events. To some observers, this signal would travel forward in time from sender to receiver, but to other observers in different reference frames, the same signal would travel backward in time from receiver to sender. The mathematics permits no ambiguity here. If faster-than-light communication exists, some observers necessarily see signals arriving before they are sent. This becomes catastrophic when you combine the perspectives of multiple observers. Using faster-than-light signals, you could construct scenarios where information about your own future reaches you before that future occurs. You could receive messages warning you not to send the very message that triggered the warning. These causal loops create logical contradictions that appear irresolvable within any coherent physical theory. Consider a concrete scenario. You send a faster-than-light message to a friend on a distant planet. From your reference frame, this message travels forward in time but faster than light. Your friend receives it and immediately sends a reply using another faster-than-light method. From certain reference frames, this reply travels backward in time. The reply arrives at Earth before you sent your original message. You now know what message you will send before you decide to send it. You could choose to not send it based on receiving the reply, but if you do not send the original message, how did your friend know to reply? These paradoxes are not mere philosophical puzzles. They represent genuine contradictions that would make physics incoherent. If causes can follow effects, the entire structure of physical law collapses. Prediction becomes impossible. The past becomes as uncertain as the future. The ordered sequence of events that allows the universe to have a sensible history dissolves into chaos. The speed of light, therefore, functions not merely as a speed limit but as a causality preservation mechanism. It ensures that cause always precedes effect for all observers. It maintains the logical structure that makes physics possible. Violating it does not merely break a record, but threatens to break the coherent ordering of events that allows the universe to have a sensible history. This is permission, not practicality, turned upside down. Special relativity does not merely forbid faster-than-light travel due to energy costs. It reveals that the very concept contains hidden contradictions about the nature of causality and time ordering that make it logically problematic, quite apart from any engineering challenges. The speed limit appears woven into reality at the deepest level. It emerges not as an arbitrary rule imposed from outside, but as a necessary consequence of how space and time relate to each other. The universe is not a stage on which events occur according to external rules. The universe is a structure whose geometry determines what events are possible, is not prohibited by a law. It is excluded by the nature of space-time itself, Yet something remarkable happened 11 years after Einstein published special relativity. In 1916, he completed a far more ambitious theoretical framework called general relativity. This new theory described gravity not as a force, but as curvature in space-time caused by mass and energy. The presence of matter warps the geometry of space and time, and other matter moves along curved paths in this warped geometry, which we perceive as gravitational attraction. Think of a heavy bowling ball placed on a stretched rubber sheet. The ball creates a depression in the sheet. A marble rolled across the sheet curves toward the bowling ball, not because the ball pulls on it, but because the sheet itself is curved. The marble follows the straightest possible path through curved terrain, which happens to curve toward the massive object. This is how gravity works according to general relativity. Mass curves space-time, and other masses follow curved paths through that curved geometry. General relativity retained everything. Special relativity established about the cosmic speed limit. Nothing can move through space faster than light. Causality constraints still apply to objects traveling through space-time, but general relativity introduced a crucial distinction that would become the foundation for all subsequent faster-than-light speculation. While objects cannot move through space faster than light, the space-time through which they move has no such limitation. Space itself can expand or contract at any rate. During cosmic inflation in the first fraction of a second after the Big Bang, space expanded so rapidly that regions originally adjacent ended up separated by distances far greater than light could have traveled in that time. This expansion did not violate relativity because nothing moved through space faster than light. Space itself carried everything along while expanding. Today, galaxies at the edge of the observable universe recede from us at velocities exceeding light speed. Light that left those galaxies billions of years ago is only now reaching Earth because the space between us has been expanding throughout that journey. Those distant galaxies are not moving through space at superluminal velocities. The space between us and them is expanding, and the cumulative effect of this expansion over billions of light years produces recession velocities that exceed 300,000 kilometers per second. This distinction between moving through space and being carried by expanding space is not a technicality. It represents a fundamental feature of general relativistic physics. An ant walking across an expanding balloon moves through the balloon surface at ant speed, but points on the balloon surface can separate from each other faster than the ant could ever walk because the balloon itself is growing. The ant obeys its speed limit, while the balloon violates nothing by expanding at arbitrary rate. This opened a door that physicists would not fully explore for nearly 8 decades after Einstein published his theory. If space can expand faster than light, carrying galaxies along at superluminal velocities relative to distant observers, might it be possible to engineer a local region of space that moves through the broader universe at faster-than-light rates? Could you create a bubble of flat space embedded in a wave of expanding and contracting space-time that propagates at arbitrary velocity? The math allows it. The universe resists it. But the math does allow it. Einstein's own equations, the field equations of general relativity, contain solutions where localized regions of space-time geometry move at speeds unconstrained by the light barrier. These solutions are exact, rigorous, mathematically self-consistent. They do not violate general relativity, they exploit it. Understanding these solutions requires grasping what a warp drive actually proposes. The idea is not to move a spacecraft through space at faster-than-light velocities. That remains forbidden by everything special relativity established. Instead, the proposal involves creating a geometry of space-time where space contracts ahead of the spacecraft and expands behind it. The ship sits in a flat region of space, experiencing no acceleration, feeling no forces, while the warped geometry around it propagates through the universe at arbitrary speed. Inside the warp bubble, nothing moves faster than light relative to its local surroundings. The spacecraft remains stationary with respect to the flat space inside the bubble, but that flat region, embedded in the surrounding warped geometry, moves through the broader universe at velocities unlimited by the light barrier. The spacecraft would sit motionless relative to the flat space inside such a bubble. It would obey all the constraints special relativity imposes on motion through space, but that local space-time region would be embedded in a propagating wave of geometry that moves through the broader universe at superluminal velocity. The spacecraft would never violate the speed limit through space. Space itself would do the moving. This does not break the limit. It relocates it. The speed constraint applies to motion through space-time, not to the motion of space-time itself. Warp proposals exploit this distinction to achieve effective superluminal travel without anything actually exceeding the speed of light relative to its immediate surroundings. The first rigorous mathematical framework for such a concept emerged in 1994 when physicist Miguel Alcubierre published a paper that would become the foundation for all subsequent warp drive research. Alcubierre showed that Einstein's field equations permit a metric, a mathematical description of space-time geometry, corresponding to exactly the kind of moving bubble described above. His solution was elegant and devastating. Elegant because it demonstrated that faster-than-light travel was not forbidden by general relativity in the way special relativity seemed to suggest. Devastating because the energy requirements for such a geometry involved forms of matter that might not exist and quantities of energy that exceeded practical imagination. The Alcubierre metric describes a region of flat spacetime surrounded by a shell of intense curvature. Ahead of this flat region, space contracts. Behind it, space expands. The net effect propels the flat region forward through the broader universe, while everything inside experiences complete normalcy. From outside, observers would see something extraordinary. Such a bubble would cross interstellar distances in times that seemed impossibly short to external observers. When the bubble dissipated and the spacecraft emerged, it would have effectively traveled faster than any light signal could have completed the same journey through normal space. Yet the occupants would have experienced nothing unusual. No acceleration, no time dilation beyond what they started with, no crushing gravitational forces. They would simply have been carried along by the geometry of space-time itself, passengers on a wave that space creates and space carries forward. This is permission, not practicality. General relativity permits such geometries. Einstein's equations accept them as valid solutions, but permitting something mathematically differs enormously from permitting it physically. The equations of motion permit many configurations that nature never realizes. The question is not whether the math works, but whether the universe provides any way to actually create such configurations. But before exploring those requirements and why they matter, we must understand what makes the Alcubierre metric work at a deeper level. What does it mean to compress space in front of a ship and expand it behind? How does curved space-time geometry produce motion without acceleration? And why does this configuration avoid the causality problems that doom naive faster-than-light concepts? These questions lead into the heart of general relativistic geometry, where intuition fails even more completely than in special relativity. Space is not empty, nothingness through which objects move. Space is a dynamic medium that can be stretched, compressed, and curved by the presence of mass and energy. And that dynamic medium might be manipulated, at least mathematically, into configurations that make the impossible merely improbable. The compression of space ahead of a warp bubble means that distances in that direction shrink. A journey of 100 light-years might involve crossing only a tiny amount of actual space if that space has been sufficiently compressed. The expansion behind the bubble stretches the space already traversed, effectively lengthening the distance between the ship's starting point and its current position as measured through normal space. The net effect creates a wave that propagates through the broader space-time geometry. This wave carries its flat interior along, like a surfboard riding an ocean swell. The surfboard does not move through the water. The wave moves through the water, and the surfboard rides the wave. Similarly, the warp bubble does not move through space. Space-time geometry propagates, and the bubble rides that propagation. The causality implications of such travel remain hotly debated. Some physicists argue that warp bubbles would create the same paradoxes as other faster-than-light mechanisms. Others suggest that the specific geometry of warp bubbles might avoid these paradoxes through mechanisms not yet fully understood. The question remains open, adding uncertainty to already enormous physical barriers. But the price tag attached to this apparent loophole in physics reveals something profound about the universe's determination to guard its cosmic speed limit through layers of constraints that make solving one problem simply exchange it for several worse ones. The math allows it, but the universe appears to resist it through multiple independent mechanisms, any one of which might prove insurmountable. Space-time is not a stage. This single conceptual shift separates general relativity from everything that came before. In Newtonian physics, and even in special relativity, space and time provided a fixed backdrop against which events occurred. Objects moved through an unchanging geometric arena. The arena itself remained passive, uninvolved, merely providing the coordinates against which motion could be measured. Einstein's general theory demolished this picture entirely. Mass and energy do not merely exist within space-time, they shape it. A massive object like our Sun does not pull planets toward it through some invisible force acting at a distance. Instead, the Sun's mass curves the space-time around it, and planets follow the straightest possible paths through that curved geometry. These paths, called geodesics, appear curved from an external perspective because the space itself is curved. The planets are not accelerating in any meaningful local sense. They are coasting through warped terrain. Think about what this means. When you drop a ball, it does not fall because Earth pulls on it. It falls because Earth's mass has curved the space-time around our planet, and the ball follows the straightest possible path through that curvature. That path happens to lead toward Earth's center. The ball experiences no force in any meaningful local sense. It simply follows the geometry of space and time as shaped by our planet's mass. This geometric interpretation of gravity has been confirmed by countless experiments. Light bends around massive objects exactly as curved space-time predicts. During solar eclipses, astronomers have measured starlight, deflecting around the Sun by precisely the angle general relativity calculates. Clocks run slower in strong gravitational fields, precisely as the theory requires. Atomic clocks aboard GPS satellites tick faster than identical clocks on Earth's surface because they experience weaker gravity. The GPS system would fail within hours without corrections based on general relativistic time dilation. Gravitational waves, ripples in space-time geometry itself, have been directly detected from colliding black holes and neutron stars. These waves stretch and compress space as they pass through it, and instruments sensitive enough to detect changes smaller than the width of a proton have confirmed their existence exactly as Einstein predicted. General relativity is not a speculative framework. It represents our most precisely tested theory of gravity and spacetime. The field equations that govern this theory relate the distribution of mass and energy to the curvature of spacetime. On one side of Einstein's equation sits a mathematical object describing space-time curvature, a tensor that encodes how distances and times relate to each other throughout the geometry. On the other side sits a mathematical object describing the energy and matter present, another tensor that specifies where mass concentrates and how energy flows. The equation states that these two objects are proportional, linked by fundamental constants. Tell the equation where the matter is, and it tells you how space curves. Tell it how space curves, and it constrains what matter could produce that curvature. This bidirectional relationship opened possibilities that Einstein himself never explored. For decades, physicists used the field equations in one direction only. They started with known matter distributions, like the mass of a star or a planet, and calculated the resulting space-time geometry. This approach produced solutions for black holes, expanding universes, and gravitational waves. Each solution described how reality behaves given specific physical circumstances. What Miguel Alcubierre realized in 1994 was that these equations work equally well in the opposite direction. Instead of starting with a known distribution of matter and solving for the resulting space-time geometry, you could start with a desired geometry and solve backward for what matter distribution would produce it. This approach, called reverse engineering the metric, allows physicists to explore what kinds of space-time configurations are mathematically consistent with general relativity. Alcubierre began with a simple desire: a bubble of flat space-time that moves through the broader universe at arbitrary velocity. Inside the bubble, physics operates normally. Space is uncurved. An observer experiences no acceleration. Nothing strange happens locally. Time passes at normal rates. The laws of physics work exactly as they do anywhere else in flat space-time. But the bubble itself, embedded in the surrounding space-time, propagates at faster than light speed relative to distant observers. The geometry he derived has become known as the Alcubierre metric, or the warp drive metric. It describes a region of flat space surrounded by a shell, where space-time curvature becomes extreme. Ahead of the flat region, space contracts violently. Space expands equally dramatically. The net effect pushes the flat region forward through the broader universe, while everything inside the flat region experiences complete normalcy. Visualizing this requires abandoning intuitions about three-dimensional space. Imagine a two-dimensional surface, like a rubber sheet representing a slice through space-time. The warp bubble appears as a peculiar distortion moving across this sheet. The distortion carries a flat region along with it, like a surfboard riding a wave. Matter inside the flat region does not move relative to the local rubber surface, but the distortion itself propagates across the sheet at whatever speed the geometry supports. A more intuitive analogy involves walking on a moving walkway at an airport. You stand still on the walkway. Your feet do not move relative to the walkway surface beneath them, but the walkway carries you forward through the terminal building. Now imagine a walkway that can move at any speed whatsoever, even faster than you could ever run. You still stand motionless on its surface. You obey your personal speed limit, but the walkway transports you faster than that limit would otherwise allow. The warp bubble works similarly, but in the fabric of space-time itself. The spacecraft sits motionless relative to the flat space inside the bubble. It obeys all the constraints special relativity imposes on motion through space, but that local space-time region is itself embedded in a propagating wave of geometry that moves through the broader universe at superluminal velocity. The spacecraft never violates the speed limit through space. Space itself does the moving. The contraction ahead of the bubble is crucial. Space being compressed in the direction of travel means distances in that direction shrink. A journey of 100 light-years might involve crossing only a small amount of actual space if that space has been sufficiently compressed. The destination that seemed impossibly distant becomes effectively closer because the intervening space has been squeezed into a smaller volume. The expansion behind the bubble serves a complementary purpose, stretching the space the bubble has already traversed so that the starting point recedes rapidly. From outside the bubble, observers would see something remarkable. A spacecraft departing Earth would seem to stretch and blur as it entered the warp field, its light becoming increasingly redshifted as the bubble accelerated. Then it would vanish entirely as the bubble achieved superluminal velocity. No light from the interior could escape to reach external observers once the bubble moved faster than light relative to its surroundings. The bubble would cross interstellar distances in what appeared to external observers as arbitrarily short times. A journey to Alpha Centauri might take days or hours from the perspective of those watching from Earth, depending on how fast the bubble propagated. When the bubble stopped and the spacecraft emerged, it would have traveled faster than any light signal could have completed the same journey through normal space. Yet nothing inside the bubble ever exceeded light speed relative to its local surroundings. The spacecraft sat motionless with respect to the flat space inside the warp bubble. Astronauts aboard would feel no acceleration, experience no time dilation beyond what they started with, detect no unusual forces. They would simply have been carried along by the geometry of space-time itself. Passengers on a wave that space creates and space carries forward. This is what distinguishes warp proposals from naive faster-than-light concepts. The speed limit applies to motion through space-time. It does not apply to the propagation of space-time geometry itself. Just as cosmic expansion carries distant galaxies away from us at superluminal recession velocities without anything moving through space faster than light, a warp bubble would carry its contents across the cosmos while obeying all local speed constraints. The mathematics checks out. Alcubierre's metric is an exact solution to Einstein's field equations. It does not approximate or contradict general relativity. It exploits general relativity, using the theory's own structure to construct geometries that achieve effective superluminal travel through means the theory permits. The equations accept this solution as readily as they accept the solution for a black hole or an expanding universe. But having written down the desired geometry, Alcubierre then performed the calculation that would haunt warp drive research for decades. He plugged his metric back into Einstein's equations and solved for the matter distribution that would produce such a geometry. The question was simple. What kind of stuff would you need to create a warp bubble? The answer proved devastating. The warp bubble requires negative energy density. Not low energy, not zero energy, negative energy. A quantity less than the vacuum of empty space. This exotic matter would need to possess gravitational properties opposite to everything we have ever observed. Normal matter causes space-time to curve in one direction, creating the attractive gravity we experience every day. Exotic matter with negative energy would curve space-time the opposite way, creating gravitational repulsion. To understand why this matters, consider what the warp bubble geometry demands. The contraction of space ahead of the bubble requires something pushing space together from ahead. The expansion behind requires something pulling space apart from behind. Normal matter cannot do this. Normal matter creates attractive gravity that would work against the required geometry. Only matter with negative energy density could produce the repulsive gravitational effects needed to compress space ahead and expand it behind. The physics of negative energy is not entirely unknown. Quantum mechanics predicts that certain configurations can produce regions of negative energy density. The Casimir effect provides the clearest example. When two uncharged parallel metal plates are placed extremely close together in a vacuum, they experience an attractive force pushing them together. This force arises because quantum vacuum fluctuations between the plates are restricted compared to the fluctuations outside. The restriction creates a region between the plates with slightly negative energy compared to the surrounding vacuum. This effect has been experimentally measured and confirmed. But there exists an enormous gap between the tiny negative energy densities achievable through known quantum effects and the quantities required for a functional warp bubble. The Casimir effect produces negative energy densities on the order of a few millionths of a joule per cubic meter. Alcubierre's original calculations suggested the warp field would require negative energy equivalent to the mass energy of a star. Converting that to familiar units means negative energy densities trillions upon trillions of times larger than anything quantum mechanics provides. Subsequent refinements reduced this estimate somewhat. Physicists discovered that the geometry of the warp bubble could be optimized to reduce energy requirements. Thinner bubble walls required less exotic matter. Certain shapes proved more efficient than others. But even optimistic calculations require negative energy quantities, vastly exceeding anything quantum mechanics might provide. The improvements brought requirements down from stellar masses to planetary masses to perhaps mountain masses, still impossibly beyond reach. Moreover, the quantum effects that produce negative energy come with strict limitations that appear fundamental. The quantum inequalities discovered by physicist Lawrence Ford and others demonstrate that negative energy densities must be balanced by positive energy densities nearby. Nature seems to demand that any negative energy be paid back with interest. The more negative the energy density in a region, the briefer it can persist before positive energy must compensate. The larger the region of negative energy, the more positive energy must appear somewhere nearby. These constraints appear to prevent macroscopic regions of sustained negative energy density from existing. You can borrow negative energy from the quantum vacuum, but the loan comes due almost immediately and with steep interest rates. The math allows it. The universe resists it. The warp drive therefore faces its first layer of impossibility. The geometry is mathematically valid. Einstein's equations permit it without complaint. But producing that geometry requires matter with properties that might not exist in sufficient quantities or configurations. The exotic matter needed appears to violate the quantum inequalities that govern how negative energy can manifest in physical reality. This distinction between mathematical permission and physical feasibility cannot be overstated. General relativity is a permissive theory. Its equations accept many solutions that describe physically unrealizable scenarios. Time travel solutions exist within general relativity. Geometries connecting distant regions of the universe through shortcuts called wormholes exist as valid solutions. Configurations where space rotates and allows closed time-like curves, paths through spacetime that loop back to their own past, exist mathematically. All of these are mathematically consistent with the field equations. None of them imply that physical reality actually contains such structures, or that engineering could create them. The Alcubierre metric belongs to this category of solutions that the mathematics permits, but physics may forbid. It demonstrates that general relativity does not fundamentally prohibit effective faster-than-light travel in the way special relativity prohibits objects moving through space faster than light. But it immediately encounters physical constraints that may be equally insurmountable. This is permission, not practicality. Beyond the exotic matter problem, subsequent analysis revealed additional barriers that compound the difficulty. The warp bubble creates a horizon around its contents similar to the event horizon of a black hole. This horizon separates the flat interior from the warped exterior in ways that severely constrain communication and control. Consider the challenge of steering. A spacecraft inside a warp bubble cannot send signals to the bubble wall to adjust its direction. Why not? Because signals from the interior cannot reach the warped region ahead of the bubble. That region is effectively superluminal relative to the interior. Light signals from the spacecraft race toward the bubble wall at 300,000 kilometers per second, but the wall ahead of them recedes faster than light. The signals can never catch up. The bubble proceeds on its initial trajectory with no mechanism for course correction. Once the bubble forms and begins propagating, its contents are committed to whatever path was set at the start. Navigation becomes impossible. If an obstacle appears ahead, if the destination has moved, if any adjustment is needed, the occupants have no means to make it. They are prisoners of the geometry they created. The problem of stopping proves equally severe. How does a warp bubble decelerate? The occupants cannot manipulate the geometry surrounding them because their signals cannot reach it. They cannot send instructions ahead to collapse the bubble because ahead is precisely the direction from which they are isolated. Some mechanism would need to operate from outside the bubble, but arranging such external intervention for a superluminal bubble traveling across interstellar distances presents obvious practical impossibilities. Who would position themselves at the destination to stop the bubble? How would they know when it was arriving? How could they coordinate with occupants they cannot communicate with? Each question reveals deeper problems. The isolation that allows superluminal travel also prevents any reasonable method of controlling that travel. These control problems are not engineering challenges awaiting clever solutions. They emerge from the fundamental geometry of the warp bubble itself. The same properties that allow the bubble to propagate at superluminal speeds isolate its interior from any ability to influence its trajectory or velocity. The physics that permits the motion forbids controlling it. You cannot have one without the other. Causality concerns also reappear despite the local compliance with speed limits. While nothing inside the bubble moves faster than light relative to local spacetime, the bubble itself enables travel between distant points faster than light signals could manage through normal space. This creates the same potential for causal paradoxes that doom other faster-than-light proposals. If warp travel is possible, you could in principle travel to a distant location faster than light. Then travel back using conventional means before a light signal from your departure could arrive. You would arrive home before news of your departure. From certain reference frames, you would return before you left, or You could use a second warp bubble for the return journey, making the paradox even more acute. Round trips at superluminal speeds create scenarios where causes follow effects, where you could warn your past self not to take the trip. The same causal loop problems that afflict all superluminal travel schemes reappear when applied to warp bubble journeys between distant points. The warp drive cleverly sidesteps the local speed limit. It does not sidestep the causality issues that faster-than-light travel inevitably creates. Some theorists have proposed that the formation of a warp bubble might itself prevent these paradoxes, perhaps through quantum gravitational effects that would destroy any bubble about to create a causal violation. The universe might protect itself from paradox through mechanisms we do not yet understand. Others suggest that warp bubbles might only be usable along certain paths that do not allow paradox construction, restricted like one-way streets, to prevent the circular routes that create contradictions. These proposals remain speculative and unresolved. They represent hopes rather than solutions. The causality problem remains one more barrier in a growing list of constraints that the warp drive concept must overcome. The energy requirements for warp bubbles have been revised repeatedly since Alcubierre's original paper. Each revision has attempted to bring the impossible requirements closer to something imaginable. Though success has proven limited, original estimates suggested the warp field would require negative energy equivalent to the mass energy of the observable universe. Subsequent work by physicist Chris van den Broek showed that clever geometry could reduce this to stellar mass equivalents. Converting that to energy through Einstein's famous equation yields a number with more zeros than fit comfortably on a page. Subsequent work by physicist Chris van den Broek showed that clever geometry could reduce this requirement substantially. By making the warp bubble very small on the outside while maintaining a large flat region inside through extreme space-time curvature, the energy budget could drop to the mass equivalent of a few solar masses. Still impossibly large, but progress. Later calculations by physicist Harold White at NASA suggested that certain oscillating configurations might require only hundreds of kilograms of negative energy. This brought the requirement down by factors of billions from original estimates. If true, it would make the energy budget at least discussable, rather than obviously absurd. These reductions, while dramatic, do not change the fundamental problem. Even a single kilogram of negative energy exceeds by enormous factors what any known physics can provide. The quantum effects that produce negative energy operate at scales billions of times too small. The Casimir effect generates negative energy densities measured in millionths of joules. Scaling these effects to kilogram quantities would require technologies and physics currently indistinguishable from magic. Moreover, the optimistic estimates rely on assumptions about warp bubble configurations that may not survive more detailed analysis. Each claimed reduction has been challenged by other researchers who identify overlooked factors or calculation errors. The true minimum energy requirement remains uncertain and controversial. What is certain is that it vastly exceeds anything achievable through known physics. The Alcubierre drive therefore represents a proof of concept rather than a practical proposal. It demonstrates that general relativity's structure permits configurations that would achieve effective superluminal travel. It shows that the cosmic speed limit is not enforced by general relativity in the absolute way special relativity suggests, but it does not demonstrate that such configurations can be physically realized. The distance between mathematical permission and physical implementation may be infinite. This doesn't break the limit, it relocates it. The exotic matter requirement is one constraint. Control and navigation represent others. Causality preservation adds more. Each barrier stands independently, and solving one does not automatically solve the others. The universe's determination to prevent effective faster-than-light travel manifests not as a simple wall, but as a layered defense system. Yet the theoretical exploration continues. Physicists are stubborn creatures, and the allure of faster-than-light travel motivates persistent effort despite repeated disappointment. If exotic matter with negative energy density cannot be created in sufficient quantities, might other approaches achieve similar geometric effects through different means? Could space-time curvature be manipulated through mechanisms that do not require negative energy? These questions drove research that would eventually produce refinements, attempting to eliminate the exotic matter requirement entirely. Recent proposals have claimed to construct warp-like geometries using only positive energy, the ordinary matter and energy that fills our universe. These claims have generated excitement and media coverage, suggesting breakthroughs have occurred. Such attempts represent the frontier of warp drive theory, the region where mathematical possibility presses against physical reality with increasing force. Each proposed solution to one problem tends to reveal new problems lurking beneath. The universe appears to guard its speed limit through layers of constraints, with every loophole opening onto deeper barriers. Understanding these recent proposals requires examining what happens when physicists attempt to construct warp geometries using only positive energy. The results illuminate something profound about the relationship between mathematics and physical reality. They reveal that the cosmic speed limit is not enforced by a single barrier, but by an interlocking network of constraints that become more restrictive the harder you push against any one of them. The math allows it, the universe resists it. This pattern repeats at every level of analysis. Solutions that work mathematically encounter physical barriers. Proposals that overcome physical barriers create new mathematical problems. The constraints interlock like puzzle pieces, each one holding others in place. Remove one, and the others shift to fill the gap. What emerges from attempts to achieve warp geometry without exotic matter is not a path toward faster-than-light travel, but a deepening appreciation for why such travel appears fundamentally incompatible with the structure of past, physical reality. The exotic matter problem seemed like the warp drive's single point of failure. Solve that problem, many physicists reasoned, and the path to faster-than-light travel would open. This assumption motivated decades of theoretical work, attempting to construct warp-like geometries using only positive energy, the familiar kind of matter and energy that fills our universe. What these efforts revealed was something more sobering than continued impossibility. They revealed that the exotic matter requirement was actually holding other, worse problems in check. Think of it like removing a wall from a house to create an open floor plan. You might discover that wall was load-bearing, supporting the entire roof. Remove it without installing alternative supports, and the structure collapses. The exotic matter requirement functions similarly within warp drive physics. It represents one constraint among many, and its removal does not simplify the problem but rather exposes deeper structural issues that the exotic matter constraint was somehow masking. Recent theoretical proposals have explored various approaches to eliminating negative energy from warp drive solutions. Some involve modified space-time geometries that redistribute energy requirements across different configurations. Others examine whether quantum vacuum effects might provide the necessary curvature without exotic matter. Still others investigate whether modified theories of gravity might permit warp-like solutions with different energy constraints altogether. These proposals must be understood for what they are: theoretical refinements exploring the mathematical boundaries of general relativity, not breakthroughs, bringing warp travel closer to reality. None have demonstrated physical feasibility. The distinction matters enormously for understanding what these proposals actually achieve. One class of proposals involves what physicists call subluminal warp drives, geometries that produce warp-like effects at speeds below the light barrier. These solutions can sometimes be constructed with positive energy alone, avoiding the exotic matter requirement entirely. The logic seems promising at first glance. If you can build a slow warp drive with ordinary matter, perhaps scaling up to superluminal speeds becomes tractable through gradual refinement. The problem is that the transition from subluminal to superluminal configurations is not continuous. Geometries differ in fundamental ways that become apparent only upon detailed analysis. A subluminal warp bubble maintains causal connection between its interior and the surrounding space. Light signals can pass between inside and outside. Control remains theoretically possible. Information can flow. A A superluminal bubble severs this connection entirely, creating horizon structures that change the physics in ways that cannot be smoothed over. The bubble interior becomes causally isolated from everything external. No signal from inside can reach the boundary. No external influence can affect the interior. Whatever energy advantages subluminal solutions might offer do not extend to the superluminal regime. The mathematics that works below light speed fails above it. Building a slow warp drive teaches you nothing useful about building a fast one, because the two problems are fundamentally different. This is not a matter of degree but of kind. Other proposals have examined whether particular arrangements of positive energy might produce the necessary space-time curvature through sophisticated shaping and timing. These approaches, sometimes called engineered space-time solutions, attempt to use the nonlinear nature of Einstein's equations to achieve effects that seem to require exotic matter in simpler configurations. Einstein's field equations are highly nonlinear, meaning that combinations of solutions do not simply add together like numbers. Two gravitational fields combined produce effects beyond just the sum of their individual effects. This nonlinearity creates mathematical complexity, but also mathematical opportunity. Perhaps clever arrangements could exploit nonlinear effects to achieve warp-like geometry without exotic energy sources. The mathematics occasionally appears to cooperate with such efforts. Certain arrangements of positive energy density can produce local regions of space that contract or expand in ways resembling what a warp bubble requires. The contraction ahead and expansion behind can be generated individually using known physics. The challenge lies in orchestrating these regions into a coherent warp bubble that moves faster than light while maintaining stability. When physicists attempt this orchestration, new constraints inevitably emerge. The configurations that produce local contraction tend to require expansion elsewhere. The expansion regions require contraction nearby. The energy flows needed to maintain dynamic geometry generate their own gravitational effects that interfere with the intended configuration. Each solution to one problem creates two more problems demanding solutions. One particularly stubborn barrier involves the Hawking chronology protection conjecture. Stephen Hawking proposed in 1992 that the laws of physics conspire to prevent the construction of time machines, even when specific configurations seem to permit them. While never proven rigorously as a mathematical theorem, the conjecture has accumulated substantial theoretical support over 3 decades of investigation. Attempts to construct closed time-like curves, paths through space-time that loop back to their own past, consistently encounter instabilities that appear to destroy the configuration before the causality violation can occur. Quantum effects near the region where time loops would form generate intense radiation that disrupts the geometry. The vacuum fluctuations that normally hover near the threshold of detectability become amplified to destructive intensity precisely where chronology protection matters most. Superluminal warp bubbles face similar problems because they create similar causality concerns. A bubble enabling travel between points faster than light could manage through normal space implicitly creates the potential for causality violations. Travel to a distant star faster than light, return at subluminal speed, and you can arrive before news of your departure. The same round trip using 2 warp bubbles makes the paradox more acute. The mechanisms that prevent time machine formation could destabilize warp bubbles, attempting superluminal travel through exactly the same physics. The universe appears to defend causality through redundant mechanisms that activate whenever superluminal configurations approach formation. The math may allow the geometry, but quantum physics destroys it before it can violate causality. Quantum effects near the bubble boundary provide the most studied such mechanism. Calculations show that the extreme spacetime curvature at a warp bubble's edge would generate intense Hawking-like radiation. This radiation resembles what black holes produce at their event horizons, but potentially far more intense due to the extreme curvature gradients involved. Particles would be created from the vacuum in enormous quantities as the boundary between normal and warped spacetime formed. This particle creation drains energy from whatever source maintains the warp configuration. For superluminal bubbles, where the energy requirements already strain credibility, This additional drain could become so severe that it destroys the bubble before it achieves its intended purpose. The radiation would not simply weaken the bubble. It would concentrate at precisely the regions where geometry must be maintained most precisely. The boundary layer where space transitions from contracting to flat to expanding represents the most delicate part of the configuration. Quantum radiation would attack this boundary preferentially, disrupting the structure where disruption matters most. The radiation problem illustrates a pattern that repeats throughout warp drive research. Classical general relativity permits certain exotic configurations without apparent objection. The field equations accept warp bubble geometries as valid solutions. But quantum mechanics then imposes additional constraints that make those configurations unstable or unrealizable. The marriage of quantum theory and general relativity, incomplete as our understanding of quantum gravity remains, consistently closes loopholes that classical physics alone leaves open. This pattern suggests that a complete theory of quantum gravity, which we do not yet possess, would impose even more severe constraints on exotic spacetime configurations. Every time physicists have combined quantum mechanics with another branch of physics, the combination has proven more restrictive than either theory alone. Quantum gravity should prove no exception. Another class of recent proposals explores whether modifications to general relativity itself might permit more tractable warp solutions. These modified gravity theories introduce additional terms or mechanisms to Einstein's equations, often motivated by attempts to explain dark energy or dark matter without invoking unknown substances. Some of these theories predict different relationships between energy and spacetime curvature that might favor warp bubble formation. Within certain modified gravity frameworks, warp-like geometries might require less exotic matter, or none at all. The mathematics in some cases appears to support this possibility quite elegantly. Papers have been published showing that specific modifications to general relativity permit warp solutions with positive energy alone. Headlines have proclaimed breakthroughs, excitement has generated, but modified gravity theories face their own severe constraints that temper any enthusiasm. They must reproduce all the successful predictions of general relativity, while somehow permitting warp configurations that standard general relativity forbids. This proves extremely difficult in practice because the modifications affect everything, not just warp drives. General relativity has been tested to extraordinary precision across multiple regimes. Gravitational wave observations from merging black holes match Einstein's predictions with remarkable accuracy. GPS satellite corrections depend on general relativistic calculations that must be correct to nanoseconds or the system fails. Mercury's orbital precession, a phenomenon that baffled physicists for decades before Einstein, matches general relativity's predictions exactly. The deflection of starlight by the sun during eclipses confirms the theory's geometric interpretation of gravity. Any modified theory must agree with standard general relativity in all these tested regimes, while somehow differing in the specific regime relevant to warp drives. The modifications must be precisely tuned to affect only configurations that have never been tested while leaving unchanged all configurations that have. This seems suspiciously convenient, like proposing a law of physics that applies everywhere except where we can check. The modifications that permit easier warp solutions tend to also predict observable differences in other contexts. Different orbital precession rates, different gravitational waveforms, different light deflection angles. These predicted differences would already have been detected if the modifications were real. Experiments have not detected them, which constrains the modifications to increasingly narrow windows of possibility. Theories that survive experimental constraints tend to reproduce general relativity's predictions so closely that they offer no practical advantage for warp drive construction. The window of viable modified gravity theories that both match observations and permit easier warp solutions appears to be vanishingly small, if it exists at all. The math allows it, the universe resists it through experimental constraints on any modification that would help. The energy focusing problem presents another fundamental barrier that proves extremely difficult to circumvent. General relativity requires that energy focuses geodesics, causing them to converge toward each other. This is why matter causes gravitational attraction. This is why things fall down. This is why stars collapse when they exhaust their fuel. The focusing of geodesics by positive energy density represents one of the theory's most fundamental features. The focusing theorem constrains how energy can be distributed in ways that directly oppose warp bubble geometry. A warp bubble requires spacetime that defocuses geodesics in front of the bubble, spreading them apart to create the contraction of space that compresses distances ahead. But positive energy focuses geodesics. It pulls things together rather than pushing them apart. This defocusing requires energy that violates the standard focusing conditions, which is another way of saying it requires exotic matter with negative energy density. The focusing theorem essentially states that you cannot contract space ahead of a moving object using positive energy alone. The geometry physically requires something that pushes rather than pulls, and positive energy always pulls. Proposals to eliminate exotic matter must somehow achieve defocusing while respecting the focusing conditions that positive energy obeys. This seems impossible on its face, and detailed analysis confirms the apparent impossibility. You cannot make positive energy behave like negative energy through clever arrangement, any more than you can make water flow uphill through clever plumbing. Some theoretical work has explored whether quantum vacuum fluctuations might achieve the necessary defocusing without violating classical energy conditions. The Casimir effect demonstrates that quantum mechanics can produce small regions of negative energy. After all, perhaps sophisticated arrangements of quantum vacuum states could cumulatively produce the required geometry through quantum rather than classical means. The quantum inequality constraints discovered by physicists Lawrence Ford and Thomas Roman close this loophole with mathematical rigor. These inequalities show that any negative energy produced by quantum effects must be compensated by positive energy elsewhere, with the compensation requirements becoming more severe for larger regions and longer durations. You can borrow negative energy from the quantum vacuum, but the debt comes due almost immediately, and with interest. The larger the region of negative energy you create, the more positive energy must appear nearby to compensate. The longer you try to maintain negative energy, the faster the compensation requirements grow. Nature enforces a strict accounting that prevents macroscopic negative energy regions from persisting long enough to be useful. The quantities of negative energy achievable through known quantum effects fall short of warp drive requirements by factors that cannot be overcome through clever engineering. The gap is not a few orders of magnitude that improved technology might bridge. The gap is 20 or 30 orders of magnitude, comparable to the difference between the mass of an atom and the mass of a planet. No plausible extrapolation of current physics closes such a gap. Recent theoretical proposals, some published only in the past few years, have claimed to construct warp solutions using only positive energy. These papers have generated media coverage, suggesting that breakthroughs have occurred. Headlines announce that scientists have found a way around the exotic matter problem. Excitement builds, hope rises. Careful analysis of these proposals reveals the pattern that has characterized warp drive research from the beginning. Solving one problem introduces others that may be even more severe. The constraints interlock in ways that become apparent only through detailed examination. Each apparent victory turns to ashes. Upon closer inspection, one widely discussed approach involves constant velocity warp drives, configurations that maintain a fixed velocity rather than accelerating or decelerating. These solutions can sometimes be constructed with positive energy, avoiding the exotic matter requirement. The mathematics works out cleanly. The geometry is consistent. The energy conditions are satisfied. The catch is that such bubbles must always have existed and must continue existing forever. They cannot be created from flat space using positive energy. They cannot be dissipated back into flat space using positive energy. They represent eternal features of space-time that either exist from the beginning of time or do not exist at all. This might seem like a minor technicality, but it represents a fundamental practical barrier. A warp bubble that cannot be created or stopped is not a transportation system. It is a permanent feature of space-time geometry that either exists somewhere in the universe or does not. Even if such bubbles exist naturally, perhaps formed during cosmic inflation or through other cosmological processes. We could not construct one to carry us between stars. We could only hope to find one and somehow board it without being able to stop it at our destination. The constant velocity solutions also cannot accelerate or decelerate. They move at fixed speed forever. A bubble moving at 10 times light speed toward Alpha Centauri would continue past Alpha Centauri at 10 times light speed, never stopping, never slowing, carrying its passengers on an endless journey through the cosmos. This is permission, not practicality, taken to absurd extremes. Another approach involves soliton solutions, self-reinforcing warp geometries that maintain their shape while propagating like waves that never dissipate. These solutions elegantly solve certain mathematical challenges. The soliton maintains itself through its own internal dynamics, requiring no external support once established. The geometry is stable against small perturbations. The mathematics possesses aesthetic beauty, but soliton solutions encounter the same practical barriers as constant velocity configurations. Creating a soliton from flat space, accelerating it to useful velocities, steering it toward a destination, and stopping it upon arrival all require operations that positive energy alone cannot perform. The soliton exists as a mathematical object of remarkable elegance that physical reality cannot instantiate from scratch. The stability problem compounds these difficulties in ways that become more severe as solutions become more sophisticated. Warp bubble geometries exist in delicate balance even when mathematically valid. Small perturbations tend to grow rather than dissipate. The extreme curvature at bubble boundaries amplifies any imperfections exponentially. Imagine a pencil balanced perfectly on its point. Mathematically, this configuration is an equilibrium. The forces balance. The pencil can, in principle, remain balanced forever, but the slightest perturbation, the tiniest vibration, the gentlest breath of air topples the pencil. The equilibrium is unstable. Physical reality cannot maintain it. Warp bubble geometries resemble this balanced pencil, but in multiple dimensions simultaneously. Quantum fluctuations, gravitational waves from external sources, thermal vibrations in the matter generating the field, internal asymmetries in the configuration, any of these could seed instabilities that rapidly destroy the geometry. The bubble would not gently deflate, it would catastrophically collapse, releasing enormous energy in ways that would prove fatal to any occupants. Classical general relativity cannot fully analyze stability for these configurations, because the extreme curvatures involved require quantum gravitational effects that we do not yet fully understand. Our mathematical tools break down precisely where we most need them. But what analysis is possible suggests that stability poses challenges more severe than the exotic matter problem it supposedly replaced. The energy configurations that might theoretically produce warp geometry appear to be unstable equilibria, requiring perfect conditions that physical reality cannot provide. Thermal fluctuations alone would destabilize most proposed configurations within microscopic timescales. Maintaining a warp bubble long enough to travel interstellar distances would require control, precision, exceeding the quantum uncertainty limits that physics imposes on all measurements. This doesn't break the limit, it relocates it from exotic matter to stability. The constraint has moved, not disappeared. Solving the exotic matter problem has revealed that stability represents an equally fundamental barrier, and stability interacts with other constraints in ways that compound the difficulty. The horizon problem grows more severe as solutions attempt to avoid exotic matter. Warp bubbles inherently create causal disconnection between interior and exterior, regardless of what energy sources them. Signals from inside cannot reach the bubble boundary in time to affect its behavior. This disconnection creates fundamental barriers to navigation and control that do not depend on what type of energy maintains the bubble. For subluminal bubbles, this disconnection is partial. Some communication remains possible between interior and exterior. Control signals can in principle reach the bubble boundary. Adjustments can theoretically be made. navigation remains at least conceivable. For superluminal bubbles, the disconnection becomes complete and absolute. The bubble interior becomes causally isolated from everything outside, including any control systems that might attempt to guide or stop it. Light signals from inside the bubble cannot catch up to the boundary ahead because the boundary moves faster than light. The interior exists in its own isolated causal pocket, unable to influence or even communicate with the external universe. Some proposals suggest that the bubble configuration itself could be pre-programmed with a specific trajectory before departure. The geometry would contain encoded instructions that unfold automatically, guiding the bubble to its destination without requiring real-time control. The bubble becomes a ballistic projectile, aimed at a target rather than a steerable vehicle. This approach faces obvious and severe objections. How do you navigate unknown space without the ability to adjust course? Interstellar space is not empty. Dust, gas, rogue planets, stellar wind, magnetic fields, gravitational anomalies, any of these could affect a journey. A pre-programmed trajectory calculated from billions of miles away cannot account for conditions discovered along the way. What happens if the destination has moved? Stars orbit the galactic center. Planets orbit stars. A journey to a planet around Alpha Centauri might take years even at superluminal speeds. The planet will have moved substantially in its orbit during that time. A pre-programmed trajectory aimed at where the planet was when you left would miss where the planet is when you arrive. What about obstacles appearing in the path? A comet passing through your trajectory, a previously undetected asteroid, debris from some cosmic collision. Any of these would prove catastrophic for a bubble unable to alter course. The pre-programmed trajectory becomes a suicide, run through unknown territory with no possibility of evasion. The collision problem adds yet another layer of concern that becomes more troubling upon detailed analysis. A warp bubble traveling through normal space encounters all the matter and radiation in its path. Interstellar space is not perfectly empty. It contains roughly 1 atom per cubic centimeter on average, plus cosmic rays, photons, neutrinos, and dark matter. A journey of several light years would encounter enormous quantities of material. What happens to this material when it contacts the bubble boundary? The physics here becomes extremely uncertain because it involves regimes we have no experience with. Some calculations suggest the material would be swept up and accumulated at the leading edge of the bubble, compressed by the contracting space ahead into increasingly dense concentrations. By journey's end, the bubble would arrive at its destination surrounded by a shell of interstellar matter compressed to extreme densities and heated to enormous temperatures. The energy in this compressed shell could exceed nuclear weapons by factors limited only by journey distance. Arriving at your destination would mean arriving with a weapon of planet-destroying power aimed at whatever you were visiting. Other analyses suggest the material would be deflected around the bubble rather than accumulated. The extreme space-time curvature might redirect incoming matter, like water flowing around a rock. But even this more optimistic scenario involves extreme energy releases. The deflection process itself would generate intense radiation. Matter accelerated around the bubble boundary at near-light speeds would produce gamma rays, particle showers, and other hazardous emissions. Either outcome poses serious problems for practical travel. Safe arrival seems impossible under either scenario, and any radiation produced by matter interactions with the bubble would affect observers along the journey path. A warp bubble crossing interstellar space might leave a trail of destruction behind it, irradiating everything it passed with lethal intensity. This observation leads to broader concerns about the implications of warp technology, even if it could somehow be developed. A warp bubble is fundamentally a weapon of unprecedented power, regardless of its intended purpose. The space-time distortions involved could devastate planetary surfaces. The energy releases upon arrival or termination could exceed anything in human arsenals. Even a failed or unstable warp experiment could produce catastrophic effects extending across astronomical distances. These concerns remain theoretical because warp drives remain theoretical. No one has demonstrated ability to manipulate space-time at macroscopic scales, No experiment has approached the energy densities involved. The concerns are projections based on physics rather than observations of actual effects, but they illustrate why physicists approach the subject with caution despite its science fiction appeal. The technologies that might enable star travel could also enable destruction on scales that make nuclear weapons look trivial by comparison. The universe's apparent determination to prevent faster-than-light travel might reflect deep principles that preserve not just causality, but something resembling cosmic safety. Perhaps the speed limit protects us from ourselves. The pattern that emerges from decades of warp drive research is unmistakable and sobering. Every solution to one problem introduces new problems. Remove exotic matter requirements, and you face stability barriers. Solve stability challenges and control impossibilities emerge. Address control concerns and causality constraints appear. Work around causality problems and quantum instabilities materialize. The constraints operate as an interlocking network rather than independent obstacles that might be defeated one at a time. This pattern suggests something profound about the relationship between mathematical solutions and physical reality. General relativity's equations permit many configurations that cannot actually exist in the physical universe. The theory is too permissive, accepting solutions that other physical principles forbid. The mathematics lacks the constraints that nature imposes. Warp drives appear to fall into this category of mathematical possibilities that physical reality excludes through mechanisms operating at deeper levels than classical geometry alone can address. The equations permit warp bubbles. Quantum mechanics forbids stable ones. Classical gravity allows superluminal configurations. Causality preservation destabilizes them. The field equations accept exotic geometries. The focusing theorems prevent their construction. The theoretical refinements exploring warp geometry are not wasted effort despite their disappointing conclusions. They illuminate the structure of space-time, the relationship between energy and curvature, and the constraints that govern what configurations physical reality permits. They teach us about physics, even though they do not teach us how to travel to the stars. Each failed attempt to circumvent the speed limit reveals new connections between apparently separate physical principles. Exotic matter relates to focusing theorems. Stability connects to quantum fluctuations. Control limitations emerge from horizon structures. Causality protection links to chronology enforcement. The web of constraints becomes more visible with every attempt to break through it. But these efforts also teach humility. The universe has guarded its speed limit for as long as the universe has existed. Every theoretical assault on that limit has revealed deeper defenses. The confidence that human ingenuity will eventually overcome these barriers may itself be a form of hubris, an assumption that we are special enough to achieve what physics seems determined to forbid. The math allows it. The universe resists it. This phrase summarizes decades of research into a single uncomfortable truth. Mathematical permission exists. Physical possibility does not. The gap between them may be infinite, unbridgeable by any conceivable advance in technology or understanding. This pattern of deepening constraints reveals something profound about the fundamental architecture of physical reality and humanity's place in a cosmos that permits us to imagine journeys we appear unable ever to take. The mathematics permits faster-than-light travel. The physics forbids it. Between these two truths lies something profound about the nature of reality and humanity's place within it. The journey through warp drive proposals has not brought us closer to the stars. It has revealed why the stars may be forever beyond our reach through any shortcut, no matter how clever our theories become. This conclusion demands reflection rather than resignation. What does it mean that Einstein's own equations contain solutions describing geometries that would achieve effective superluminal travel? Yet those geometries appear impossible to create. What does it mean that every attempt to remove one barrier reveals deeper barriers lurking beneath? What is the universe telling us through this pattern of deepening constraints? The relationship between mathematical possibility and physical reality has puzzled philosophers and physicists since ancient times. Plato believed mathematical forms represented a deeper reality than physical objects, which merely approximated the perfect geometric ideals existing in some abstract realm. A circle drawn on paper is imperfect, but the mathematical concept of a circle possesses perfect precision. Plato thought the mathematical concept was more real than any physical instantiation. Modern physics often seems to support this Platonic view, with mathematical equations predicting phenomena long before experiments confirm them. Einstein derived special relativity from mathematical reasoning about the constancy of light speed before any experiment demonstrated time dilation. Paul Dirac predicted antimatter existence from the symmetries of his equations years before positrons were discovered in cloud chambers. The mathematical structure seemed to know about physical reality before physicists did. Yet the warp drive phenomenon suggests a more complicated relationship between mathematics and physics. Mathematics describes a vastly larger space of possibilities than physics realizes. General relativity's equations accept countless solutions that describe configurations involving closed time-like curves, traversable wormholes, infinite energy densities, naked singularities, and other exotic structures. Physical reality appears to contain none of these, despite the equations welcoming them without objection. The equations do not distinguish between realizable and unrealizable solutions. They treat the Alcubierre metric with the same mathematical validity as the Schwarzschild metric describing ordinary black holes. Both are exact solutions, satisfying every requirement the field equations impose. Both emerge from the same mathematical framework with equal legitimacy, yet one describes objects astronomers observe throughout the cosmos, while the other describes something that may be fundamentally impossible to construct. This asymmetry reveals that general relativity, despite its extraordinary success at predicting observable phenomena, does not provide a complete description of physical reality. Other principles constrain what configurations can actually exist beyond what the field equations alone specify. Some of these additional principles emerge from quantum mechanics. Others may reflect aspects of nature we do not yet understand, or have not yet formulated into precise mathematical language. The equations provide necessary conditions for physical existence, but not sufficient ones. A configuration must satisfy Einstein's field equations to be physically possible, but satisfying those equations does not guarantee physical possibility. Additional filters operate that the classical equations do not capture. The mathematics is too permissive. Reality is more selective. The pattern of deepening constraints in warp drive research suggests that these additional principles operate in layers rather than as a single barrier. Remove one obstacle and others appear. Solve those and still others emerge. The universe appears to defend its structure through redundant mechanisms, ensuring that certain configurations remain impossible even when specific barriers are overcome. This redundancy itself reveals something important about cosmic architecture. If only one constraint prevented faster-than-light travel, clever physics might eventually find a way around it. A single lock can be picked, a single wall can be scaled, but the existence of multiple independent constraints, each separately capable of forbidding warp configurations, suggests that faster-than-light travel is not merely difficult, but fundamentally incompatible with the deep structure of reality itself. The constraints are not independent accidents. They connect to each other through principles that become visible only when you try to circumvent them. Exotic matter requirements link to focusing theorems. Focusing theorems connect to energy conditions. Energy conditions relate to stability requirements. Stability requirements involve quantum fluctuations. Quantum fluctuations tie to causality preservation. Each thread leads to others in a web of mutual reinforcement. Consider what a universe permitting practical faster-than-light travel would actually require. Causality would need to operate differently, perhaps with some events having no definite temporal ordering relative to each other. The clear sequence of cause-preceding effect that makes physics predictive would blur into ambiguity. Quantum mechanics would need modification to avoid the instabilities that destroy exotic energy configurations. The focusing theorems relating energy to geodesic behavior would need exceptions that somehow did not propagate into observable contradictions elsewhere. Each of these changes would have implications far beyond warp drives, affecting every other aspect of physics in ways difficult to predict. The cosmic speed limit is not an arbitrary rule imposed on an otherwise permissive universe like a traffic regulation that could be repealed without broader consequence. It represents a consequence of the unified structure that makes physics coherent. Violating it would unravel that coherence in ways that would affect everything else we understand about physical law. The speed limit is a load-bearing wall in the architecture of reality, not a fence that might be removed without structural consequence. Remove it, and the building collapses. The structure exists as a unified whole, where each part supports the others. You cannot change one principle without changing everything that principle connects to, and the speed of light connects to almost everything. This perspective transforms how we should understand warp drive research and the decades of theoretical effort invested in it. The work exploring these configurations is not wasted effort toward an achievable goal that keeps frustratingly receding. It represents a sophisticated probe of the universe's fundamental structure, using impossible constructions to illuminate possible principles. Each constraint discovered teaches us something about the deep principles governing physical reality that we might not learn any other way. The impossibility of warp drives is itself a discovery of profound importance, revealing connections between causality, energy, geometry, and quantum mechanics that might not be apparent through any other line of investigation. We learn about what is possible by carefully mapping what is not. The math allows it. The universe resists it. This phrase captures something essential about the relationship between human theoretical imagination and physical reality. We can conceive configurations that reality excludes. We can write equations describing spaces that cannot exist. The gap between conception and existence opens a window onto the principles that govern which conceptions correspond to possibilities. The human desire to reach the stars runs deep in our species. Since our ancestors first looked up at the night sky and wondered what those points of light might be, we have asked what lies beyond our small world. The campfire speculation of prehistory became the systematic astronomy of civilizations, which became the astrophysics of the modern era. Each advance revealed a universe larger and stranger than the previous generation imagined. The scale of the universe, progressively disclosed through centuries of astronomical discovery, seems almost designed to mock the desire that prompted our inquiry. Stars visible to naked eye observation lie at distances requiring thousands of years to traverse even at light speed. The nearest neighboring star system would take over 4 years to reach if you could travel at the cosmic speed limit, which you cannot. Neighboring galaxies stand millions of light years away, utterly beyond any conceivable human journey through normal space regardless of how much time you were willing to spend. Warp drives promised an escape from this cosmic imprisonment that distance imposes. If space itself could be manipulated rather than merely traversed, the vast distances might become navigable through geometry rather than velocity. Science fiction has explored this possibility for decades, depicting civilizations that span galaxies through faster-than-light technology, as casually as we span continents through aviation. The theoretical work showing that general relativity permits warp geometries seemed to validate these dreams with the authority of mathematical physics. The equations did not forbid what we longed to achieve. Einstein himself had opened the door, even if unknowingly. Perhaps the universe was more accommodating than its vast emptiness suggested. The pattern of deepening constraints delivers a different message. The universe permits us to imagine faster-than-light travel. In exquisite mathematical detail, it permits us to write down equations describing warp bubble geometries with complete rigor. It permits us to calculate what exotic matter configurations would be required and to explore alternatives when those requirements prove problematic. But it forbids us from actualizing these configurations through every mechanism physics has discovered, operating at every level we have probed. This is not cruelty, though it may feel that way to those who dreamed of stars within reach. The constraints preventing faster-than-light travel also provide the stable structure that makes our existence possible. A universe where space-time geometry could be easily warped by engineering effort would be a universe where matter could not reliably organize into atoms, molecules, planets, or living beings. The stability of atomic structure depends on the constancy of physical law across space and time. If space-time could be casually manipulated, that constancy would dissolve. Chemistry would become unreliable. Biology would become impossible. The same rigidity that frustrates our travel ambitions enables our existence in the first place. Gratitude seems more appropriate than frustration when viewed from this angle. We exist because the universe operates according to stable principles that prevent arbitrary manipulation of its fundamental structure. Those principles also limit our travel options. But this limitation appears to be the price of existence itself. A universe we could traverse at will might be a universe we could not inhabit. The prison and the home are the same structure viewed from different perspectives. The philosophical implications extend beyond physics into questions about humanity's cosmic significance that have occupied thinkers for centuries. 19th century thinkers debated whether the vastness of the universe made it likely that other worlds harbored intelligent beings, or whether Earth might be unique in harboring life. The question consumed astronomers and philosophers alike, with compelling arguments on both sides. Modern astronomy confirms vast cosmic scales containing billions of potentially habitable worlds, while leaving the question of cosmic life frustratingly unresolved. We have not detected signals from alien civilizations. We have not found biosignatures in planetary atmospheres. The universe remains silent despite decades of listening, though absence of evidence is not evidence of absence, given the vastness involved. The speed limit places severe constraints on any answer to the question of cosmic companionship that might eventually emerge. Even if intelligent life fills the galaxy in abundance, civilizations separated by thousands of light years cannot meaningfully interact across those distances. Messages sent between distant stars require centuries or millennia for response. A conversation at such pace hardly qualifies as communication in any human sense. Coordinated activity spanning galactic distances becomes impossible when coordination signals take longer to arrive than civilizations typically endure. Each civilization, however advanced its technology might become, remains fundamentally alone within its light cone, aware of cosmic neighbors through ancient light that departed before those neighbors knew we existed, unable to establish real-time connection regardless of desire. This cosmic loneliness is not a failure of communication technology awaiting solution through engineering advancement. It reflects the fundamental structure of space-time as physics reveals it. General relativity permits us to see distant galaxies in glorious detail, but forbids us from visiting them in any reasonable time. Special relativity permits us to send signals at light speed, but forbids faster information transfer by any means yet conceived. The universe shows us its immensity in loving detail, while keeping most of it forever beyond our reach. Some find this perspective bleak beyond consolation. The cosmos teases us with wonders we cannot explore, neighbors we cannot meet, horizons we cannot cross no matter how our technology advances. Our descendants might colonize nearby star systems over geological timescales through patient multi-generational effort. But they will never span the galaxy as a unified civilization communicating in real time. The science fiction dream of galactic empires and interstellar federations appears to contradict fundamental physics rather than merely awaiting sufficient engineering. But this perspective also possesses a nobility that becomes visible upon reflection. We inhabit a universe vast beyond comprehension, governed by principles we can discover and understand despite our biological limitations, containing mysteries that will occupy human inquiry for as long as our species endures. Our light cone, though finite compared to cosmic totality, encompasses billions of stars and potentially billions of worlds waiting for exploration across timescales our descendants might actually achieve. The constraints that seem so limiting when we dream of distant galaxies also make possible the science that reveals those galaxies to our instruments. The universe of arbitrary plasticity would be a universe without reliable law, and a universe without reliable law would be a universe where science could not function. The same rigidity that confines us also empowers us to understand our confinement. The theoretical exploration of warp drives exemplifies this relationship between constraint and discovery. The mathematics is beautiful, possessing the aesthetic elegance that physicists have learned to trust as a guide toward truth. The physics is instructive, revealing connections between principles that appeared separate before the analysis began. The implications are profound, touching questions about the nature of physical law and the relationship between mathematical possibility and physical reality. We learn about space-time structure through attempts to manipulate it. We learn about energy conditions through attempts to violate them. We learn about causality preservation through attempts to circumvent it. We learn about the relationship between classical and quantum physics through attempts to exploit gaps between them. The impossibility we discover teaches us as much as any possibility could. Perhaps more, because impossibilities reveal constraints that possibilities obscure. Human civilization has faced fundamental limits before and found wisdom rather than despair in accepting them. We cannot visit the interior of the sun, but this impossibility taught us about nuclear physics and stellar evolution. We cannot observe electrons without affecting them, but this impossibility taught us about quantum mechanics and the limits of classical measurement. We cannot know the future with certainty, but this impossibility taught us about probability and the nature of time. We cannot achieve perpetual motion, and this impossibility taught us thermodynamics and the concept of entropy that governs everything from engines to ecosystems to the ultimate fate of the universe. Each impossibility initially seemed like failure, a door closed against human ambition. Each eventually revealed deep truths about the universe's structure that we could not have learned any other way. The speed limit joins this distinguished list of productive impossibilities, constraints that teach us more than their absence would. We cannot travel faster than light, and this impossibility teaches us about the relationship between space and time, the nature of causality, the structure of space-time geometry, and the principles that govern what configurations physical reality permits. This is permission, not practicality. The permission to understand why faster-than-light travel appears impossible, even when mathematics permits the geometry. The permission to learn about space-time structure through attempts to circumvent its constraints. The permission to appreciate our cosmic situation with clear eyes, rather than false hope. The search for ways around the cosmic speed limit will undoubtedly continue, regardless of pessimistic assessments. Human ingenuity has surprised us before, finding paths that seemed permanently closed. The history of physics includes many confident pronouncements of impossibility that subsequent discoveries overturned. But the pattern of deepening constraints in warp drive research suggests we may be approaching a fundamental limit rather than an engineering challenge awaiting better technology. The distinction matters enormously for setting expectations and directing effort toward achievable goals. If faster-than-light travel is merely an engineering problem, however difficult, resources should flow towards solving it. Patient work on exotic matter production, space-time manipulation techniques, and warp bubble stabilization would represent investments in a future capability worth possessing. The challenge would be technological rather than principled. But if faster-than-light travel represents a fundamental impossibility woven into the structure of physical law, we should accept that and direct our efforts toward goals that physics permits. Interstellar travel through normal space, though requiring centuries or millennia, does not violate physical law. Generation ships carrying self-sustaining communities across the void, seed ships carrying embryos or genetic information for reconstruction at distant destinations, digital mind transmission, encoding human consciousness for light-speed travel, followed by reconstruction. These approaches work within physics rather than against it. The acceptance of limits need not diminish. Wonder at what remains accessible. The universe that emerges from modern physics is strange and magnificent beyond any pre-scientific imagining, full of wonders that do not require faster-than-light travel to appreciate or explore. Space-time bends around massive objects in ways we can measure with exquisite precision. Quantum particles exist in superposition until observation collapses them into definite states through mechanisms we still do not fully understand. The vacuum of empty space teems with virtual particle creation and annihilation, a seething foam of quantum activity underlying apparently calm emptiness. Black holes puncture space-time with infinite curvature, hiding singularities behind event horizons that mark the boundary between accessible and inaccessible regions. The Big Bang created space itself, along with all the matter filling it, a beginning that was not an explosion into pre-existing emptiness, but the emergence of existence from conditions we cannot describe using current physics. Dark matter pervades the cosmos, shaping galactic structure through gravity, while remaining invisible to every instrument we have built to detect it. Dark energy accelerates cosmic expansion through mechanisms that remain entirely mysterious, despite constituting most of the universe's energy content. This universe is not the sterile clockwork cosmos of classical physics, where everything reduces to billiard balls bouncing predictably through eternal emptiness. It is dynamic, surprising, and fundamentally mysterious at its deepest levels. Human beings have discovered enormous amounts about its structure in a remarkably short time. A few centuries of systematic investigation after millennia of speculation. But we have also discovered how much remains unknown, including the quantum gravitational principles that would fully resolve questions about warp drive feasibility. The speed of light represents something deeper than a speed limit, in the sense that traffic regulations are speed limits. It represents the rate at which causality propagates through space-time, the maximum speed at which influence can travel from one event to another. It represents the conversion factor between space and time in relativistic physics, the constant that allows distances and durations to be measured in compatible units. It appears in equations governing electricity, magnetism, gravity, nuclear forces, and the structure of matter itself. Tampering with it would mean tampering with everything those equations describe. Change the fine structure constant, and you change chemistry. Change chemistry, and you change biology. Change biology, and you change the conditions permitting our existence and our inquiry. The universe we inhabit is the universe where light speed governs causality. We can imagine other universes with different rules, hypothetical realms where faster-than-light travel poses no theoretical problems, but we cannot visit such universes or even demonstrate that they could coherently exist. They remain mathematical fantasies rather than physical possibilities. The speed limit is not imposed on our universe from outside by some cosmic traffic authority. It emerges from the deep structure that defines what our universe is. A universe with a different speed of light would be a different universe in every respect, not our universe with a modified parameter. Living with the gap between mathematical permission and physical possibility requires a maturity that does not come easily to a species accustomed to overcoming obstacles through ingenuity and effort. Science fiction has trained us to expect that sufficient technological progress will overcome any obstacle given enough time and resources. The history of invention supports this optimism within limits, but some obstacles may not be technological. Some may be woven into the fabric of reality at levels no technology can address, because technology operates within physical law rather than modifying it. The cosmic speed limit appears to be such an obstacle, defended by principles that go deeper than any equation we have written or any theory we have formulated. Our species emerged on one planet, orbiting one unremarkable star among hundreds of billions in one galaxy among trillions. We have existed for an eye blink of cosmic time, appearing only in the last 100,000 years of a universe 14 billion years old. Yet in that brief span we have discovered the structure of atoms, the evolution of stars, the expansion of space, and the curvature of space-time. This achievement is remarkable regardless of whether we ever reach the stars. A universe that produces beings capable of understanding it, even partially, is a universe containing something precious. The understanding matters independent of the travel opportunities it might or might not eventually provide. The warp drive proposals teach us that the universe we can imagine exceeds the universe we can travel. Our mathematics ranges farther than our spacecraft ever will. Our theories describe configurations that our engineering cannot instantiate. The gap between conception and creation opens a window onto principles we could not discover any other way. They teach us that mathematical beauty does not guarantee physical existence. Elegant equations can describe impossible configurations with perfect precision. The aesthetic satisfaction of a beautiful theory provides no evidence for its physical realizability. Nature is under no obligation to match our sense of elegance. They teach us that constraints preserve structure as much as they limit possibility. The barriers preventing faster-than-light travel also prevent the instabilities that would make structured existence impossible. The prison walls are also the walls of home, providing shelter as much as confinement. Most profoundly, they teach us that our desire to transcend limits must coexist with acceptance that some limits may be eternal. Human ambition is admirable. Human acceptance of what cannot be changed is also admirable. Wisdom lies in distinguishing which response fits which situation. We are explorers who have discovered the boundaries of our exploration. We are dreamers whose dreams reveal the constraints that govern reality. We are creatures of curiosity, inhabiting a cosmos that satisfies that curiosity with knowledge while forbidding the journeys we most desire. The warp drive mathematics grants permission to think about the universe in new ways. Physical reality withholds permission to violate principles that make that universe coherent. Both permissions matter. Both have value. Together they define our situation more clearly than either alone could. The stars will remain distant. Light from other worlds will continue arriving bearing news of their ancient past. Human civilizations might someday orbit other suns, having traveled there through patience and generations rather than warped space. The journey will take longer than we wished. The destination will be worth the wait. We will carry with us the knowledge that shortcuts were sought and found wanting, that the cosmic speed limit stood firm against humanity's best theoretical efforts. This knowledge is not defeat. It is understanding. It is the universe revealing its structure through the very barriers it erects against our ambitions. And in that knowledge lies something valuable that transcends the disappointment of constraint. The universe is not arbitrary. It operates according to principles we can discover through careful investigation and creative theorizing. Those principles permit astonishing phenomena while forbidding others. The pattern of permission and prohibition reveals structure, and structure is what we seek when we do physics. The warp drive journey ends not at a destination among the stars, but with a map of where we cannot go and why we cannot go there. The map shows connections between causality, energy, geometry, and physical existence that we would not have discovered through any other investigation. It shows the limits of mathematical imagination when confronted with physical reality. Like all good maps, it helps us understand where we are. Even when it cannot take us where we wish to be, we stand on Earth, looking up at the stars, knowing they are forever beyond our quick reach. The light from distant suns falls on our faces as it has fallen on human faces for 100,000 years. Our ancestors looked up with wonder. We look up with understanding that they lacked, but with the same wonder undiminished. We understand why the stars are distant and will remain so. We understand why the shortcuts we imagined cannot work despite their mathematical elegance. We understand what the universe is telling us through the deepening constraints that close every loophole we discover. And in the understanding, we find something that transcends the disappointment of limitation. We find the universe revealing its deep structure through the very barriers it erects. We find physics teaching us about reality through the impossibilities it discovers. We find meaning in the exploration itself, regardless of destinations reached or unreached. The math allows it, the universe resists it. The resistance teaches us what permission alone could not. The constraints illuminate what freedoms would obscure. The impossibilities reveal what possibilities would hide. The speed of light will stand. The stars will remain distant, and humanity will continue learning, discovering, wondering at a cosmos that permits us to exist, to think, and to understand why some journeys exist only in mathematics and dreams.